In case you didn't know, Thursday is a holiday, so I will not be seeing you. There won't be any classes. And we are ready to begin. We are starting another section. We're going to look at equations of lines and planes. If you're a visual person, this is good. If you're not a visual person, maybe you're going to have to become one. So we're going to look at first what the equations of lines in 3D look like. Well, we can do this in a number of ways. One is called the vector equation of a line. The second way is called the, I think it's the component. Try to think what this textbook calls it, equation of a line. And the third one better be called symmetric, because that's what I call it. The symmetric equation of a line. Now we're talking about a line in 3D, 3 dimensions. But before we do that, let's look at a line in 2 dimensions. Wouldn't that be the equation of a line in 2D? If I rearranged it, wouldn't it also be that guy? I believe we call that the point slope equation of a line, and depends on the textbook, the standard equation of a line. But it's the same thing. Would you give algebraically, these two are identical, they're just rearranged in different orders. So you might think, oh, the equation of a line in 3D is just going to be maybe z equals 2y plus 3x. You know, it's going to have that kind of look to it. Or x plus 2y plus 3z equals 10. Maybe it's going to have that kind of look. No. If you do this guy in 3D, right, this straight line in 3D, it would look not like a line at all. What would 2x plus 3 look like in the 3D world?
A flat plate.
Yeah, it'd be a vertical flat plate, wouldn't it? On the ground, it would look a bit like y equals 2x plus 3, but wouldn't it be a a vertical flat plate? But whatever it is, it ain't a line, right? So we have to figure a different way to come up with the equation of a line. And the way that we do it is we use parametric equations. So the equation of a line in 3D is going to be given in the form of a parametric equations. It's going to be x equals 2t plus 1, y equals 3t take away 2, and z equals going to be 4 minus 2t. It's going to look like that. The parametric equation. Every line looks like that. Now, do you see it's made up of an x, a y, and a z component, and it's using, you remember the parametric stuff kind of touched on, right? That's how equations of lines are going to look like. Now, I said there's 3 versions, so let me show you what this equation looks like when it's written in these 3 versions. In the first one, can I just call it VE because I don't want to write all that again? What you do is you go 2t plus 1i plus 3t take away 2 chi plus 4 take away 2tk. Would that seem pretty equivalent? Would you say that's saying the same thing in a different way? That makes sense? So this would represent an equation of a line. If you wanted to do it in component form, you go 2t plus 1, 3t take away 2, and 4 take away 2t. And would you agree that's pretty much the same as the thing above, right? But that's going to be our component equation. So far, so good. Now, the third one, not so obvious, the symmetric equation. So there's a fair amount of work to do a symmetric equation. Right, you take this guy, and if you subtract 1 from him, you get this. And if you divide it by 2, you get that. Then you take the second equation, you add 2 to it, and then you divide it by 3, and you get that guy. And then you take the last equation, told you there's a lot of work, subtract 4, and then divide it by -2 to get that. And the way the symmetric equation works is t is equal to this, t is equal to this, and t is equal to this. So you will write down the symmetric equation and that is the symmetric equation of a line. I think these two are pretty intuitive, right? When you see the parametric equation, would you agree these two are pretty intuitive? They pretty much make sense. Would you agree this one looks really weird? This one is the least common of the three, but it does appear in some questions, so you need to know what it looks like. Do you notice that if I tell you this equation or this equation, would you agree that you could convert it into this one? Relatively straightforward, right? So if I said the vector equation is this, would you be able to convert it into that by doing these 3 steps? Right. Just call the first guy X and solve for T, call the second guy Y and solve for T, call the third guy Z and solve for T, and you get the symmetric equation of a line. Now, I haven't yet told you how to get the equation of a line. And this is how we're going to do it. To find the equation of a line, in 3D, you need to know a point on the line, let's call that point x1, y1, z1, and a direction vector. We'll call that vector v, and it can have components a, b, c. Well, let's show you why that's the only thing you need. If I wanted to know the equation of this red line, and can you imagine that this red line is shooting out like this pen is, right? It's sticking out of the board, right? It's a 3D line. If I tell you the coordinates of a point on that line, and then I tell you a direction vector is basically any vector. It doesn't matter what one it is. It doesn't need to be a unit vector, but a vector that tells you what direction to travel from P. Won't that make a line happen? Imagine you got a point like my tip of my finger. Where is it? My tip of my finger is the point. And then I tell you a vector. Won't that information be enough to create the line? So what will the equation of the line be if it passes through this point and it has a direction vector of that? Well, in parametric form, it's going to be x1 plus at, x2 plus bt, and x3 plus ct. Now notice where the numbers come from. Do you notice that the point x1, x2, x3 goes here? And do you know that the direction vector a, b, c is multiplied by t? Does that seem reasonable for how it's going to work? T is basically, if t was 2, you're 2 units away, right? T is 40, you're 40 units away, whatever, right? You're just creating it in that form. Now, if you want to write that down in one of these fellas, if I wanted to do it, for instance, this is how I would write it if we were doing component version. Now, little guy at the front. I'm going to call R of t with a little vector on it. Technically speaking, isn't this a vector that changes position according to t? And so it's a function of t, but it's not a normal function of t, it's a vector function, so we put a little r. Now, I could have called it f arrow of t, but we don't. Convention is we like the letter r. I have no idea why they chose r. I guess they chose it because it wasn't f, right? They just wanted to be different, right?
Why are we adding x3 for the z or x2 for the y instead
Is
of
it
like
x1, y1,
the y
and z1?
initial?
Oh, darn it in space. Thank you. Yeah, somebody caught, I don't know where my brain was. Yes, that makes much more sense, doesn't it? Right, so you're right. X1 plus AB, Y1 plus. Do not rush things. The moral of the story is if you rush things, you just make more mistakes. So it's the x coordinate of P plus AT, the y coordinate of P plus BT, and the z coordinate of T plus CT. There we go. We got the guy. Well, let's put this into effect. Let's start with the simplest question I can think of. Suppose I have a line that passes through the point 1, 2, -3, and it has a direction vector 1, 3, 2. Then the equation of the line in component form would be 1 plus 1t, 2 plus 3t, and that guy plus 2t. So as long as I know the point P and a direction vector 1, 3, 2, would you agree that creating the equation of the line is pretty straightforward? Would you like to see one of these guys in 3D? So let's show you what that guy looks like. In Canvas, you have got some software that I've already put there for you. Are you looking right now at a nice little helix? Right. So let's make, let's go up here and just get rid of that guy. And let's change this fella. This particular piece of software seems to have preset values, so you have to change them. Ah, darn it. I am very good at not swearing today. I'm very pleased with myself. Right, now, when you want to do this using CalcPlot 3D, it's a little bit clunky, but it does the job. Click on select, right? And of all the guys you want, pick space curve. I know it doesn't sound right, but that's what you pick, right? Pick space curve. Right. Think of Space Force. Then you would go here and you put in 1 plus t. Then you go here and you go 2 plus 3t. And then you go here and you do -3 plus 2t. With a bit of luck, t can go from 0 to 3. And then click on the little box. And then, oh, okay, my axis is miles away. Here's my little line. Do you see it? It just doesn't fit inside the axis. So I'm going to have to change the axes. What's the darn it in space. Been so long since I've done this film. I'm just trying to find the ability to. Oh, it should be in this, wouldn't it? I would think. No. Oh, that's kind of cool. A little animation. That's not what I wanted. Stop. Oh, that's pretty cool too, but it's still not what I want. Okay, somewhere in here, I should be able to. Gotcha. Okay, maybe shrink it a little bit more. There. There. Can you see our little line a little bit better now? Okay. Now I'm sure you can play about with it in other ways, but there, that looks good. I don't want that line, but evidently I made it happen. So, oh, there's your axes. There. Okay. So there's our little line. That one there is just a position vector. Pain in the butt that it's there, but can't do much about it now. So that is that guy.
Can I ask a quick question?
Yes, well.
So it seems like when we're defining this as a vector,
Yes.
which as the line that we're making isn't the vector though, it's the vector from, is it like the vector from the origin to the point at the end of the vector, and then we're just getting the line of all those points?
Yes.
So are we really, when we write it as a vector, the line isn't really the vector itself, it's just sort of like
the vector is giving you the position of each point on the line as a vector from the origin.
Okay, so when we're writing the vector, that's just, the line isn't that vector itself, it's the function of the vector that's actually the line?
I think what that means. The equation that we are drawing, the vector equation that we are writing down, let me do the picture so we can see it. The way I see this is I think of the point 1, 2, 3, and then from that point, as you change t, I move along the line. So what this is going to give me is the coordinates of any point at t. So for instance, if I found the position at 5, I would be looking at 6, 17, 7. Now that's written down as a vector. The way my brain sees that is as the coordinates of the point.
Okay.
Now, when you do a vector of the coordinates of a point, we call that vector the position vector. But this position vector is equivalent to the coordinates of the point.
Okay. That makes sense. Thank you.
Yeah. I don't even think of it as a vector, although it's written as a vector. I just think of it as a line. And I can find the equation of that line anywhere or the position of that. Now, I'll give you one more of these baby ones, then I'm going to make your brain hurt. Okay, since you're on the scope, give me 3 points for P. Keep them simple.
6.
2.
5.
Okay. And we need the direction vector. Whoa, that was weird. A whole load of stuff just fell off my table. We must have ghosts. Okay, what's V? I'm glad that you lot aren't in charge of saving the world, because by the time you press the button to fire the missile, we'd be dead. Come on, decisions. Pick something.
2.
Right,
-1.
at last, a negative.
0.
Oh, good choice. Now, you take this equation and you will get the line, and it will be 6 plus 2t, comma, 2 minus 1t, comma, 5 plus nothing t. Would you agree? Nobody would write 0t, you just write 5. So as long as I tell you the coordinates of a point and the position vector, would you agree the equation of the line is baby stuff, right? It's just plug and jug and you're done. Why is this going to blow your mind? When you do the equation of a line in 2D, once I tell you the equation of the line isn't that unique. In other words, that line only really has one equation if you write it in the form y equals, right? I mean, if you double everything, you can still, that's it. The equation of a line in 2D is unique. It is not unique in 3D. Can you imagine this is a line in 3D? If this is the point that you've got, which is 625, couldn't I choose another point on the line and it would equally give me the equation of that line? Wouldn't it just be the equation of a line at a different starting point? And what would happen then is that these numbers 6, 2, and 5 could actually be totally different numbers. For instance, they could be 8, 1, 5. The direction vector is not unique. Couldn't I double the direction vector? Couldn't I do it 4, -2, 0? Wouldn't it still be the same direction? It'd just be a vector twice as long. Which means that when you do a line in 3D, nothing is unique about that line. All the points on that line have an equation, but can't the equation be infinitely many different equations, all representing the same straight line? Does that make sense? That uniqueness has now left the building. An equation of a line in 3D could be any starting point you like, and any vector that represents that direction, or multiple of that vector. And now that I'm at that, lines in 3D have a direction to them. Wherever you are at t equals 0, t equals 1, t equals 2, t equals 3, won't you be traveling along a line in a particular direction? Right, t equals 0, I'm here, t equals 1, I'm here. So lines in 3D have a direction. So when we draw lines in 3D, it's helpful to put a little arrow on them. Of course, couldn't the line be going that way? So it is similar to 2D in the sense it's a line, but aren't they quite different in lots of other respects? So my next question we're going to do is, let's find the equation of a line, and I'm not going to ask you a lot to give me points because I'll be here to Christmas. Joining P and Q together, right? So making no attempt to be accurate. Can you pretend that's P? Can you pretend that's Q? And we're going from P to Q, right? So it does have a direction, the line. How do we find the equation of that line? Well, you need two things. You need a point on the line. And I'm picking P because I like P. And you have a direction vector V. Well, won't the direction vector V just be PQ? Would you agree? Right? P to Q, direction. So 2 take away 1, -1 take away 3, 2 take away 7. We have a point, we have a direction. So the equation of the line will be 1 plus 1t, comma, 3 minus 4t, comma, 7 take away 5t. Agreed? Using that point and this direction vector. Couldn't I also do Q as my point? And if I did Q as my point, won't the equation be 2 plus t, -1 take away 4t, and 2 take away 5t? Can you see what I mean by non-uniqueness of the answers now? Isn't that also the equation of that line? Can you see why that might cause a problem in WebAssign? That you write this one down, but it wants that one, or vice versa. I hope WebAssign is sensible and allows all equivalent answers, right? Because there could be more than one. So far, so good? Any questions?
Yeah, could you define a that same line with the vector, with like the reversed vector? So if you made the, would it still be, I mean, I know it's still the same line, but do we consider
the
it
direction
the
would
same
be
line?
different. So if you said you were doing the line from Q to P, that would be acceptable. But if they were wanting to do it, there will be an order in the question. Do the line from P to Q.
Okay, but it's still like the same line, right?
It's the same line, you're just pointing down the way instead of pointing up the way.
And same goes for like if you had a position direction vector like 2, 6, and 6, that would, if you just simplified that down to 1, 3, and 3, that would still be the same line, right?
It would still be the same line, which means WebAssign would have an even harder time because there's an infinite number of correct answers. So we will try and avoid simplifying anything just to make
Okay.
WebAssign's life easy. But yes, you could treble it as well and create another one, or minus a half it and create another one, and so on and so forth. A little bit, what's the word? Not sure what the word I'm thinking of. Coherent. Wouldn't it be nice if there was only one answer, you know, and everybody knew how to get that one answer? It does mean comparisons are a little bit difficult, because if I give you an equation of a line and you give me another equation of a line, how do we check that they're the same line, right? Because they can look quite different from each other, can't they? We will show you that there, but it is a problem. You're right. Try to find one. Oh, in case you want to do one of these guys. Wouldn't the equation be 2 plus ti plus -1, -4t j plus 2 minus 5t k? Can you also understand why I hate ijk notation? It just is clunky, but I mean, if you're asked to do it, that's what you have to do, right? I won't do the symmetric, although that does happen. Are we comfortable so far that as long as I have 2 points or a point in its direction vector, I'm good to go? So I want to do a side issue now, and it's to do with what lines can do in 3D that isn't true in 2D. So I'll try. I don't think I'm going to be successful, but I'll try. I'll call it L1, meaning line 1, and L2, meaning line 2. Is it possible for 2 lines in 3D to be parallel? Great. Is it possible in 3D for 2 lines to intersect at a point? Agreed. What are the other things that can happen with 2 lines in 3D? Because there are 2 more situations.
They can be
You might be
I thought of
thinking
something
for a
that I
word.
forgot about.
There is a name for what I think you're about to describe.
They can be skew. So
That
they,
is correct. That's the word.
because I was thinking that in 2D space, lines will only not intersect if they're parallel, but in 3D space, they can be not parallel and also not intersect. So skew, I think is, I think they're called skew if they're in
They
this
are called
situation.
skewed. Yes.
Okay.
Here is my very bad attempt to try and draw skewed. Can you imagine 2 lines not crossing, but not being parallel? I think that's actually pretty good. Does that not visually give you an idea of what I'm saying? It would be this situation, right? If you look at it carefully, do you see they don't make? This one here is kind of so obvious you probably won't get it. Couldn't it be the same line, identical lines? And won't that be more obvious in the 2D world and not very obvious in the 3D world, right? Because aren't there an infinite number of versions of the same line? You wouldn't know they were identical just by looking at them, right? You'd have to do some kind of check on it. When you see this, it's called skewed. 2 lines are skewed. These are identical. This, we would say that the 2 lines intersect. And this one here, we would say that the 2 lines are parallel. Are we comfortable with the 4 things that can happen to 2 lines in 3D space? Are there any other possible things that could happen? What do you think? Think we've covered everything that could happen? As far as I know, yes. There might be some person who comes into topology and tells me about some weird situation that no one's ever thought of. But as far as we know, these are the only 4 things that can happen. If you move into higher dimensions, like 4th dimensions or 5 or 6, some weird stuff happens. You know, but I'm not going there. So let's give you information to draw a line, but we'll make the information more and more vague. So I want the equation of a line that passes through the point 1, 4, 0. That's the easy bit. But it's to be parallel to this line. So it passes through the point 1, 4, 0, and it's parallel to that line. Now, remember what we need, a point and a direction vector. Can someone tell me how to pull out a direction vector from the information that it is parallel to that guy.
Wouldn't you just pull the coefficients off the t's?
That's what I would do. Would you agree we're good to go now? Right. So the equation of this line would be 1 plus 1t, comma, 4 minus 2t, comma, nobody writes 0 minus 4t. And there you go. I get lots of nods. We're comfortable with that particular one. Okay. Yeah, we've done that. This one needs a new piece of paper. I want the point that passes through 1, 3, negative 2. Right? And it's perpendicular. I prefer the word orthogonal. To the vector 1, 1, 3, 2, 0, 1. So it passes through the point 1, 3, negative 2, and it's orthogonal or perpendicular to these two vectors. How are we going to get the direction vector this time?
Cross product.
Agreed. I, J. Okay. 1, 1, 3, 2, 0, 1. So many I's. Take away so many J's. So many K's. And here we go. Cover that guy up. 1 take away nothing is 1. Cover this guy up. 1 take away 6 is negative 5. And cover this guy up. 0 take away 2 is negative 2. So we get a direction vector 1, 5, negative 2. And put that and that together. And we get the equation of the vector as 1 plus a t, 3 plus 5t, and negative 2 minus 2t. So if I give you a point in the direction vector, check. If I give you 2 points, we know how to get we know how to get the equation of the line join them, right? If I give you a point and I tell you it's parallel to somebody, we know how to get the equation of a line. If I give you a point and I tell you it's orthogonal to 2 guys, would you agree we could get the equation of the line? Now, I'm not going to do the next question, but we'll set it up. And I'm going to use exactly the same numbers for a reason. Passes through that point and is orthogonal to these two lines. Now, when you look at the information, these are the equations of these lines, but can't you suck out the direction vector? And if you suck out the direction vector, hopefully I did it right, isn't this guy 113 and isn't this guy 201? Do you see it's essentially the identical question that I just did a minute ago? 113 is the direction vector that was used in this line. 201 was the direction vector. Do you see it's this question? So maybe you'll be told a vector, maybe you'll be told a line, right? I don't care which of the two you tell me, because aren't you telling me the same information? Right, you're giving me a way to come up with it. So let's pause on straight lines and talk about planes in 3D. A plane in 3D is an infinite flat piece of paper. Imagine it's sloping in some direction, and then I'll try and stick in my z-axis and my x and my y. Now, it's not that rectangle. Do you know that rectangle is there just to give you an orientation idea? A plane is infinite, right? It goes this way and that way forever, right? I like it as a flat piece of paper, right? Like this, right? An infinite piece of paper. Now, what do the equations of planes look like? Well, you can't really talk about 2D because it doesn't really transfer well. The equation of a plane in 3D, thankfully, looks like that. All planes in 3D are a linear combination of x, y's, and z's equals a number. So there's not a vector form and a parametric form and a symmetric form and who knows what other form, right? There's not even different ways of writing them. They look like that, but it is not unique. The equations of a line are a little, well, they are unique in one sense that they all can be returned to the same guy. The only difference you can have between one equation of a plane and a different version of it is this thing. That is the same equation of that plane. Do you notice something that links them together?
They're all multiplied, all the terms are multiplied by 30 from the first one
Right.
to the second one.
Right, so if Will comes up with the equation of a plane and Tessa does it slightly different and she comes up with the equation of a plane and they don't look the same, won't one of them be the multiple of the other? Right, so it's not like a straight line. Don't the straight lines look totally different? Really? The numbers are different, you know, they're just different, right? You can't really tell looking at them, but you can always tell looking at an equation of a plane. If your guy's the same as mine, won't these just be multiples of each other? Okay, now, for the few minutes that we've got left, let's look at what can happen to two planes in 3D.
Can you draw two towers as well if we're going to have two planes?
Say again, Tim?
I made a bad joke.
Oh, God. Oh, no, that's not even a good joke. Right. Can't two planes be parallel in 3D space? Do you agree? If one plane is at an angle to the other, won't they intersect on a straight line? So they can be parallel, they can intersect, but if they do intersect, it will be on a line, right? A 3D line. because later on we're going to try and find the equations of this 3D line, right? When they're parallel, of course, they'll never meet. What's the third and final possibility?
Same plane.
Yeah, they're identical, right? Can you have two planes, but they're really just the same plane, right? And wouldn't that example here be an example of that? So if I said that was a plane one and this was my second plane, wouldn't they be actually identical to each other? Just like two lines can be identical, right? Now, interaction. A line in 3D and a plane in 3D. So here's my plane, one plane of each, and here's my line. Would you agree that if a line interacts with a plane in 3D, if it intersects the plane, won't it only intersect at one point? Would you agree it's impossible for the line to swing back on itself and cut through the plane a second time? Wouldn't it have to be a curve to do that? Does that make sense? That a plane, when a line hits it, only hits it once, and that's an intersection. Couldn't a plane and a line never meet? I don't know how well I've done that, but can't they be parallel? Would you get it just flies above the surface forever? There's one more possibility for a line and a plane to interact in 3D space.
They'd be, I'm not sure what the term for this is, but can it go planar? That line is on the plane.
It's on the plane. It's not the only phrase, but it's one I like using. The line is embedded in the plane, right? Can you imagine what that would look like? My flat piece of paper has a pen on it, right? Now, we're not doing other permutations, but can you imagine how three planes could interact with each other? They could be parallel to each other. Couldn't they intersect a bit like the spokes of a wheel? So the three of them could intersect on the same straight line, right? At least that's possible, right? And all the other combinations just basically build triangles of some sort. And that is us for today.